All right, hi everybody. We've heard quite a few talks this week about the potential role of globular cluster dynamics in forming some of the LIGO sources that we've observed both recently and over the past 10 years. So I'm going to sort of give an overview of some of our latest results connected to LIGO sources, but also really the main goal of this is to sort of take a step back from LIGO and think about what we actually know and sort of what are some of the key uncertainties in globular clusters in general, especially black hole populations and clusters. So I'm going to try to at least quickly touch on sort of theory, simulations, and observations related to this. Probably some of you have seen this slide. I usually start talks with this slide. I think it's sort of a useful illustration to sort of, set the stage for the key processes that are relevant for black holes that are forming and evolving in clusters, and also some of the main uncertainties. So when we think about sort of an old globular cluster like in the Milky Way, these have no massive stars, so there are no black holes being formed recently or today. So if we want to think about, the formation of black holes, we need to think about what a globular cluster would have looked like when it was very young, when it still had many massive stars close to the time that the cluster itself formed. So let's just consider a typical, globular cluster progenitor with roughly 1 million stars. So if we assume some typical initial mass function, so in our simulations, we usually assume like a Krupa 2001 IMF, we can expect roughly 1,000 stars, so 1 out of 1,000 of the entire stellar population, to be massive enough to collapse into black holes. So again, for a typical cluster, you form roughly 1,000 black holes just from the collapse of massive stars. So for a very low metallicity population, similar to the globular clusters in the Milky Way, we expect generally these lead to more massive black holes, so an average black hole mass of maybe 30 solar masses or so. So I'm putting an asterisk next to the 30 just because in a higher metallicity population, probably this mass function is shifted toward lower masses, more similar to, for example, the X-ray binary black holes we see in the Milky Way. So these black holes form relatively quickly within the first few to maybe tens of millions of years in the evolution of the cluster. So I think this part, I haven't said anything yet that is really uncertain. I think most of this is pretty secure. The first sort of key uncertain step pertains to the natal kicks that these black holes receive when they're born. So we've heard a couple of talks, especially from Adam, about how we really maybe don't know as much as we think we know on the simulation side about natal kicks, but there are lots of indications from observations. We've heard about triples and stuff showing that probably at least some black holes are born with small natal kicks. So this is key for globular clusters because globular clusters have pretty low escape velocities. Even at birth, maybe at most 100 kilometers per second for a typical average globular cluster. So you need some of the black holes to be born with low-ish natal kicks, less than 100 kilometers per second, to retain some of that initial population of black holes formed. So assuming you can retain at least some population of these black holes after natal kicks, the next key process that happens is mass aggregation. So mass aggregation happens in any sufficiently dense environment. This is a natural consequence of dynamical friction. Because the black holes are much more massive than the average star in the cluster, they naturally are going to sink to the center. So for typical cluster densities, the timescale for this mass aggregation is roughly 100 million years, within a factor of 2 or so of this. So still relatively early within the sort of 10 plus billion year lifetime of a typical cluster. So on this timescale, you have the formation of this very dense central subsystem, which is dominated mostly by the black holes. And this is sort of where all of the interesting dynamics take place that pertain to the formation of black hole binaries, formation of gravitational wave sources, et cetera. So Johan showed a sort of an illustration of this earlier. This is just to sort of give you an indication of the types of encounters that are sort of driving these processes within the black hole subsystem. So you have frequent few body encounters, so groups of small numbers of black holes that come into close gravitational contact, and they undergo these sort of resonances. And the cumulative effect of many of these resonances over time shapes the orbital properties of the black hole binaries that form, and also shapes their dynamics. So as you see here at the end, the outcome of these dynamical encounters is essentially to kick the black holes, and these are not natal kicks or gravitational wave recoil kicks. These are just simply Newtonian dynamics gravitational recoil kicks associated with these encounters. And one of the sort of consequences of these encounters accumulated over time is that the number of black holes in the cluster slowly decreases throughout the remainder of the evolution of the system, just because the black holes are kicking each other through these Newtonian gravitational interactions with one another. So over the remainder of the evolution of the cluster, the sort of typical 12 billion year lifetime, the number of black holes, which starts at roughly 1,000, decreases over time. So just to sort of illustrate this in another way, if we just plot the number of black holes versus time in the cluster, it increases very prominently early on, just from the collapse of massive stars as they evolve. It plateaus for roughly 100 million years while sort of the mass segregation process happens. After around 100 million years, the black holes have mass segregated, and now you see the number of black holes start to sharply decrease throughout the remainder of the evolution from these internal black hole dynamics. So the key question we want to ask then is, what is the fraction of black holes that are left at present day? So in this particular model I showed, they're all ejected, which would mean there'd be nothing to detect at present. But this is uncertain, and depending on the properties of the cluster, the density, how the black holes interact with stars, et cetera, you can change significantly the sort of evaporation rate of this black hole subsystem. And this is sort of the main question we want to ask is, especially thinking about observational tests of the presence of black holes in clusters, how many black holes are still here today that we could eventually observe and use as a sort of guideposts for the dynamics and presence of black holes in clusters as it might pertain to LIGO sources. Now, I should mention also that even in this, you could maybe call this maybe a pessimistic scenario where they're all ejected. Even in this case, these are still going to be contributing to LIGO sources because a subset of black hole binaries are going to be ejected from the cluster and merge much later on in the age of the universe because they have long delay times. So even if no clusters today have black holes, I don't think this is true. I'm going to show next arguments why we think many clusters have black holes today. But even in that sort of pessimistic outcome, they're still going to be contributing to LIGO sources. So I just want to add that caveat. Okay, so the next sort of few slides are looking at some sort of observational clues for the presence of black holes in clusters. And there's both a number of pieces of direct and indirect evidence for this. So sort of the first piece of motivation or evidence, you could say, for black holes in clusters came back in the late 2000s, early 2010s. So the idea here is these are black hole candidates. I'm going to talk more about what I mean by the word candidate in a little bit later. But these are black holes that are in compact orbits with luminous stellar companions. They're accreting. They're essentially typical low-mass X-ray binaries. The basic idea here is that we know from looking at both black hole and neutron star X-ray binaries in the Milky Way that black holes and neutron stars exhibit distinct fundamental planes of activity, meaning they exhibit distinct sort of locations within the radioluminosity, X-ray luminosity parameter space. And the idea is if you observe a X-ray radioluminosity for a given source, without any independent constraints, dynamical constraints on the mass of the object, you can infer or maybe make a suggestion that this object is a black hole as opposed to a neutron star just by the relative value of the X-ray and radioluminosities. So there's now been a handful of these observed in a few different Milky Way globular clusters, and there's also a handful observed in some extragalactic globular clusters as well. So Tom Macron is the expert in the audience now on this stuff, so chat with Tom and me later if you're interested about these. But this was sort of the first piece of evidence that some clusters might contain black holes. Now, this process is uncertain, and again, I'll talk about this a little bit later. None of these X-ray radio sources have dynamical mass measurements, which is really the most convincing way to say this is a black hole as opposed to a neutron star or something else. So these are candidates. They're maybe suggestive of being black holes, but they're certainly not legitimate, bona fide, black hole observations. I would say the first true confirmation of a black hole in cluster came more recently. So this was in 2018. This was from some observations with the MUSE integral field spectrograph. So essentially they did a broad radio velocity survey of a number of different Milky Way globular clusters and to look for radio velocity variability, essentially. And in one particular cluster, NGC 3201, which I should mention is a fairly unremarkable cluster. It's kind of puffy. It has a large core, maybe its most remarkable feature, but it's a very, very typical Milky Way globular cluster. In this cluster, they found a star that exhibited very large radial velocity variation. They did multi-epoch observations, which enabled them to piece together the full orbit of the star. And they inferred the presence of a basically hidden companion with a minimum mass of around 4.4 solar masses. So I'll circle back to this later. Radial velocity alone only gives you a constraint on the mass function of the black hole. You can't break the degeneracy between the true mass and the inclination. So we know the minimum mass, but again, because this is in an old globular cluster where there really are no massive stars, the turn-off mass is about 0.8 solar masses. This is clearly a black hole. There's really no other conceivable explanation for what this source could be, even if it is truly this minimum value. So you can kind of think about this as sort of the analog of these sort of Gaia black holes that have been found, but in a globular cluster. You could also think about this as maybe sort of the in-cluster analog of Gaia BH3, which is found in presumably in a disrupted globular cluster, like we heard about earlier. I'm not going to go into detail on these other two sources too much, but after this first detection, there were one, maybe two additional sources. I think one is quite convincingly a black hole. This one is maybe a little bit more uncertain because it has a bimodal orbital solution. But there's now two, maybe three black hole candidates all observed in this one single Milky Way cluster through radial velocity measurements. So aside from these sort of direct detections of black holes, there's also indirect indications. So a lot of recent work, stuff that I've done and many others as well, many of whom are in the room, has shown that globular clusters, when they contain these very dense subsystems of black holes in their centers, are dynamically governed by the interactions going on in these black hole subsystems. So this is showing surface brightness profiles of all of the Milky Way globular clusters. And very broadly, these can be sort of grouped into two distinct types. So NGC 32.1, the black hole host, is a sort of classic example of a non-core collapse cluster. It's very well fit by what we call a king profile. It has this very prominent flat component in its brightness profile in the inner region, which is what we call the core of the cluster. So most clusters look like NGC 32.1. They have large, well-resolved cores. About 80% of clusters have cores. The other roughly 20% of clusters look like, this is just one example, NGC 6397. These core collapse clusters. So here the brightness increases all the way toward the center, at least as far in as we can resolve it. And we think these two sort of different classes of clusters are essentially distinct dynamical types in terms of the features that are going on. And explaining why most clusters are not core collapse and only a subset are core collapse has been sort of a long-standing question in the field of cluster dynamics. And a lot of recent work has shown that the action of black holes and the sort of internal heating of the black hole dynamics within the center of these clusters provides a very natural explanation for why most clusters are not core collapse today. Essentially, as black holes interact with each other through those sort of few body encounters like I showed on the previous slide, they also are interacting with stars, and they're constantly transferring energy to the stars, which essentially heats the cluster from the inside, puffs up the core, and delays the onset of core collapse over time. And a really interesting sort of thing to note is all of those black hole candidates I mentioned on the previous slide, both the X-ray and radio candidates and also the radial velocity sources, these are all found in clusters with resolved cores. So that's maybe interesting, perhaps not indicative, but it's suggestive of the role of black holes in these clusters. I'm also highlighting Omega Cen here. Omega Cen doesn't have a stellar mass black hole candidate, but it does have this IMBH that's been observed now through HST astrometry, which came out about a year and a half ago, which is very exciting. Presumably, IMBHs can heat a cluster in a way somewhat analogous to stellar mass black holes. So black holes seem to be playing a role in many clusters. Again, because most clusters have these well-resolved cores, we think most clusters are consistent with having many black holes, at least dozens probably today, in their centers. Very quickly, I'll mention core collapse clusters. So there's lots of other sort of indications about sort of the interesting things that can happen in core collapse clusters. These are very distinct pulsar populations, millisecond pulsar populations in particular. So I want to highlight just one kind of interesting core collapse cluster, NGC 1851. So this is maybe potentially another black hole candidate. So this was found a couple of years ago. So this is a black hole candidate in an orbit with a millisecond pulsar that's found through pulsar timing. And this was really exciting when it was announced because the mass function for this black hole is roughly consistent with being a mass gap source and also consistent with the merger remnant masses for a number of double neutron star binaries that LIGO has seen. So people have speculated this might be a sort of low mass black hole or maybe a massive neutron star that was formed from a binary neutron star merger. Again, because this is found in a core collapse cluster, we think this is consistent with a cluster that's ejected all of its black holes, And there's a very dense population of neutron stars in the center doing interesting things. Okay, so, I'm doing good on time. So another way we can sort of look at this, distinct from the surface brightness profiles, is just sort of showing in cluster mass versus half-light radius parameter space all of the Milky Way globular clusters. A lot of recent work by myself and Claire and Carl and Felia and Newland, many people here, we've sort of developed this large catalog of cluster simulations using the cluster Monte Carlo code CMC. This has been really important for not only explaining properties of Milky Way clusters, but potential contribution of clusters to the LIGO rate, et cetera. So the main thing I want to highlight here is this sort of catalog of models is sort of very nicely spans the parameter space of observed Milky Way globular clusters at present day. And this is really important because I think, Milky Way clusters are incredibly well observed from many different perspectives. And this really provides the best observational, guideposts for us when we're sort of thinking about the evolution of clusters over time, is what we observe for the present day globular clusters. But we observe globular clusters in essentially all types of galaxies, and in particular, massive elliptical galaxies are very robust homes of globular clusters. So this is now showing in the background in gray, all of the globular clusters are observed in the Virgo supercluster. So there's tens of thousands of globular clusters observed here. And you can see here that although the overall distribution is roughly consistent with the Milky Way population, it peaks at a mass of around 10 to the 5 solar masses or so. Typical radius is around 2 or 4 parsecs. The tails of this distribution are filled out just because you have such a larger sample. So in particular, it's very distinct. You'll see up in the upper parts, you have this population of hundreds of very massive clusters that are simply not included in the Milky Way just because we only have 150 galactic globular clusters. So this sort of suggests that if we want to think about the role of clusters in forming gravitational wave sources, we also need to think about the role of these very massive clusters. This is especially important for thinking about hierarchical mergers because the massive clusters have very high escape velocities. There may be better sites or they're sort of more conducive to retaining hierarchical mergers that are subject to these gravitational wave recoil kicks. So a recent result from just a few months ago was the simulation of sort of one of the first 10 million body globular clusters with CMC. Is shown by the star in the parameter space. And this is sort of the motivation of this is to sort of span this very massive tail of the distribution of globular clusters that we see in other galaxies. So this is some work. So Aiden, where's Aiden? Yeah, so Aiden's a student at UCSD who's been leading this work. Aiden has a poster also you can look at to learn some more about this. But essentially the goal of this was to look at the role of this very massive cluster in forming black hole merges and what are sort of the implications, especially for forming hierarchical events. So this is a cluster at when it's sort of initiated as an escape velocity of over 200 kilometers per second, which is substantially over a factor of 2 or 3 higher than a typical globular cluster. So right away you can expect this is going to be really valuable for forming lots of hierarchical mergers. The kind of cool result we saw is the most massive black hole we formed in the simulation was around 250 solar masses, which was a 5th generation black hole formed through a very extensive series of hierarchical merger events over time. Collectively, this one single cluster produces over 1,000 black hole mergers over its lifetime. For perspective, that sort of list of simulations shown on the previous slide, those yellow points, the full sort of catalog of Milky Way-like clusters, produce maybe 10,000 mergers in aggregate. So this one single cluster is producing of order 10% of the entire sort of sample of globular clusters that we've simulated so far. The other really important result is that over 90% of the mergers that are happening in this very massive cluster are occurring inside the cluster itself as opposed to being ejected. So again, this is just because of its very high escape velocity. And related to this as well, over a third of the mergers in this cluster are 2nd generation or higher. So a significant fraction of the mergers when you go to these very massive clusters are able to be retained and merge again. So this is just showing M2 versus M1 for all of the black hole mergers that we see in this cluster. We're coloring by the different generation. And then the yellow stars are just the 10 most massive LIGO events observed so far. So clusters like this are very naturally capable of producing very massive black hole mergers via hierarchical mergers. Okay, so the most massive LIGO event that's been observed so far is 231123. So from a mass perspective, we're able to produce things like this. But let's think about some other implications as well, or some other sort of tests of this source. So we'll look at spins first. So this is showing chi effective, but it tells the story just as well as looking at the spins. So of course, because this is a dynamical formation channel, the chi effective distribution peaks at 0. Everything is isotropic. We generally expect equal numbers of aligned and misaligned sources. We assume in this model that all first generation black holes are born with 0 spin. So any spin that we're inducing comes from repeated black hole mergers, essentially. So initially, the distribution is all entirely 0. As you start to have second generations come into play, forming these black hole mergers that have a spin values peaked at 0.7, you have the chi effective distribution broaden. But then what we see happen is that as you start to undergo third, fourth, fifth generation mergers, the chi effective distribution starts to narrow again, essentially because you're going into the regime where you're now throwing pebbles onto a boulder. It's hard to spin up things much more than 0.7 once you build up this initially massive black hole. So generally, and this is a sort of case in point for this sort of one single fifth generation black hole we see, it has a relatively low spin compared to 231123. So it's not impossible to produce very high spins. You could imagine a scenario where you get lucky and you're having black hole mergers that are in the plane of the orbit of the initial spin. But generally speaking, I think it's challenging to produce very high spins via these hierarchical mergers. I just want to make a quick advertisement for Felia's talk. She's going to discuss some other cluster formation scenarios that might allow you to form high spins for massive events via accretion channel, but something distinct from the typical hierarchical channel. The delay time distribution is also a little bit of a challenge for forming 231123 events, which was, of course, observed in a very local universe. So this is just showing total merger mass versus merger time, assuming the cluster was born roughly 12 billion years ago. And very clear thing that you can see is the most massive events, including these hierarchical mergers, are all happening very early in the evolution of the cluster. So I saw this plot initially, I was a little surprised because you might think, well, hierarchical events, they have to sort of necessarily have a delay time between each generation because you have to wait for each generation to happen and then it has to pair up again with another black hole, et cetera. But this is not actually the case. And the main reason for this is simply because as you build up these massive black holes, more massive black holes have a larger cross-section for pairing up with other black holes, so they pair up more quickly. More massive black holes mass radiate back to the center of the cluster more quickly where they can pair up again. More massive black holes have shorter gravitational wave inspirals time. So essentially all these factors conspired to basically produce very short delay time distributions for these most massive black holes, even though they have to progress through these multiple generations. So this is a challenge for 231123-like events, because in order to produce something like this in the local universe, essentially it means the cluster must have formed relatively recently, which is possible, but perhaps a challenge. Oh, it's coming back. It's coming back. Yeah. Okay, here we go. Okay. So this slide is showing. The point of this is to illustrate the very special role of these massive clusters in the overall distribution of black holes formed in globular clusters. So the blue curve is the overall mass function of globular clusters that we observe, again, in Virgo. So again, the median cluster mass is around 10 to the 5 solar masses, a little bit higher. But when we weight this curve by the number of black hole mergers and also by the number of hierarchical mergers in the models, we see the distribution gets shifted quite pronounced to the most massive clusters. So just to illustrate this, if we look at the number of black hole mergers in each of these cluster masses, we see that the 50th percentile, or basically half of all black hole mergers occurring in globular clusters, occur in the 92nd percentile of the globular cluster mass function. So the very most massive globular clusters are contributing the most to the cluster mass function. And this becomes even more pronounced when we look at the hierarchical mergers. So this is simply because the number of mergers, and especially the number of hierarchical mergers, scales quite steeply with the cluster mass. So even though these massive clusters are relatively rare, they sort of exhibit an outsized impact on the contribution to the overall merger rate. Okay, so thinking about hierarchical mergers, we naturally might ask about these two recent events, 241011, 241110, that are sort of the best evidence yet on the LVK side for hierarchical mergers. So can these form in a massive cluster like this? So maybe this isn't surprising, but clearly these really aren't well explained by this type of model. The main reason for this discrepancy is this is a very low metallicity cluster simulation where we're assuming the black holes formed are generally higher mass simply because of reduced wind mass loss. If we want to form events like this, we really need to think about formation in more high metallicity clusters that would potentially form lower mass black holes. We actually have an example of sort of an analogous cluster to this very massive 10 to the 7 star cluster that was run previously. So this is from a project that Carl led, looking at some connections with fire galaxy simulation. So this is a roughly comparable mass cluster, 10 to the 7 solar masses, but near solar metallicity, about 0.7 solar metallicity. And again, just because of the sort of assumptions about the black hole mass function is dependent on metallicity, you can see very clearly that the mass function of black holes is shifted to much lower values. And these are much more naturally able to produce hierarchical events, which are the light blue color ones here, similar to these two recent LIGO events. Okay, so the main point that I sort of want to emphasize, this might be my last point, is that I showed before that when we look at the clusters in the Virgo supercluster, old low metallicity globular clusters are certainly very well observed. It's very well motivated to look at simulations like this. But these very young, high metallicity massive clusters are actually also very well motivated observationally. And we have a lot of reasons to sort of think that these could be both observed and also contributing to the LVK rate. So this is just one example. This is just this is from about 2007, 15 years ago. This some Keck observations of the M82 starburst galaxy. So within this cluster, I'm just highlighting here the most massive superstar clusters observed in this galaxy. And this is here showing, again, these same young superstar clusters in the same cluster mass, half-light radius parameter space. So these are all have ages of 10 million years or less. They're very high metallicity. And the main point of this plot on the bottom left, these have properties very consistent with the properties of both Milky Way clusters and also these mini massive clusters that we observe in Virgo. So this shows, one, that massive clusters like this exist with properties similar to Milky Way globular clusters, meaning that all the same dynamics we think about for old globular clusters should be operating for these young, high metallicity analogs. But this also places really interesting constraint on the birth properties of globular clusters for our simulations, which is actually really useful because, generally speaking, the birth properties of clusters are one of the main open questions. We observe old globular clusters very well. Young clusters are a little bit harder. So this is just showing the mass function of clusters now for a few different galaxies that have these young clusters observed in them. And the main punchline you can see, especially for the antennae galaxies, which are known to be a very rich source of current star formation, they have a cluster mass function that extends all the way up to these things that are well over a million solar masses. So very massive million to 10 million solar mass clusters are formed at both low and high metallicities. These are very well motivated observationally. So this is a recent paper from Claire that's sort of touching on some of these main points. So this is now showing in black. This is the observed distribution from LIGO. So this is detected. This is adjusted for sort of detectability biases. So this is sort of a non-detection biased distribution of the primary masses that LIGO has seen so far. And then this is showing in blue essentially our prediction for the local universe sample of black hole mergers coming from globular clusters, taking into account these young globular clusters that we observe at high metallicities in the local universe. So these, of course, were born more recently, so they still have many black holes because they're young. And the prediction here, of course, there are many uncertainties, but the prediction is that it's very likely that many and possibly even most of the black hole mergers in the local universe that are formed in dense star clusters are actually low mass because they're coming from these higher metallicity globular cluster analogs that we observe. I should probably wrap up. So I have a few other open questions about sort of what we know about masses of globular clusters, black holes and globular clusters, but maybe I'll let people ask questions about this and we can have some discussion. So thanks. I'll get started on my conclusions.
I have two questions, but I'll just ask one for now. You were talking about simulating low metallicity old clusters to represent things like the Virgo cluster and considering things that are more massive. But when we actually look at nearby elliptical galaxies, a lot of the globular clusters there are very close to solar metallicity. Have you done any simulations of things like that?
In Virgo?
Yeah. Yeah, if you look at like M87, the metal-rich mode, it's a little bit less than solar for the peak of that mode, but it's nothing like the Milky Way typical metallicity.
But even so there's the red and the blue populations. Yeah. The blue populations are quite low metallicity. I mean,
blues
not
are,
as low as. So yeah, there certainly are.
But the big difference per unit stellar mass is from the red ones.
Yeah, but even the red ones are still low metallicity compared to solar, no?
There's a tail that is actually super solar, and the peak of that mode it's less than solar, but it's way higher than the typical Milky Way one. Okay. So when you said low metallicity, what were you simulating?
I'm talking about things that are 10 to the solar is sort of what I'm thinking about.
10 to solar, okay.
Metallicity. So yeah, anyway, that'd be fun to chat about is sort of the...
Yeah, like for the X-ray sources, they're really skewed towards the redder mode.
Oh, good. Okay. So, yeah, that'll be good to think about. Okay. Yeah, cool.
Thanks for this really nice talk. Very clear. I was wondering if you could comment more on the time delay distributions of the high metallicity clusters, since the black hole masses are smaller.
Okay.
What sorts of, because you were saying that these like super high generation ones and the low metallicity clusters have very short time delays because they're super massive, but in the low metallicity clusters, do you see a similar trend?
Yeah, so I think it's always going to be true that the
high
most...
metallicity clusters, sorry.
Yeah, I got you. So the most massive black holes in the cluster, whether it's high or low metallicity, the timescales depend on what is the most relatively massive black hole in the cluster. So even, for example, in, we saw in this cluster, it's higher metallicity, it still forms many of these massive black holes through hierarchical mergers, actually some other channels as well. These are all going to generally be merging earlier on, just because, again, more massive things are going to have shorter delay times for a number of reasons, both related to the gravitational wave inspiral and also the cluster dynamics. But the difference, maybe this is clear. So the difference is that even if this merges very early in the evolution of the cluster, because the cluster itself was born relatively recently, the merger would happen in the local universe.
Hey, Kyle, Reed Essick from CETA. Thanks for the great talk, and I apologize if you've said this. You covered a lot of material. So the more massive clusters contribute a healthy amount, a healthy fraction of the overall mergers that you're seeing in sort of your cluster simulations. Are those also more likely to host an IMBH, though? Which then I think I've heard will kill the rate? Like, is there a sweet spot where you're massive enough to not probably have an IMBH?
Okay, so, yeah, that's a great question. So the most massive Milky Way cluster, so the open circle right up here, is Omega Cen, which has an IMBH. So we have one data point for massive clusters like this hosting an IMBH. So it could be the case that all massive clusters have IMBHs, which I don't know that I'm willing to jump to the conclusion immediately that that will kill the merger rate. Tentatively, that seems to be what things are suggesting. But I think the bigger question is, what is the sort of occupation fraction for clusters with massive black holes? I mean, I think it's probably reasonable that so Omega Centauri there's a lot of evidence showing it's a stripped dwarf nucleus, which is maybe more consistent with having a massive black hole just because galaxies have massive black holes in their center. But probably not all these massive globular clusters are stripped dwarf nuclei. So it's open to question whether or not how many of these would have massive black holes in their center. Yeah.
Hi, Kyle. Lieke van Son, Radboud University. You showed some really cool 2D plots later on where both high and low metallicity, M1, M2. And I was wondering how much you trust the structure in these distributions, specifically on the mass ratios, because I still have stuck in my mind second generation mass ratio 0.5, first generation in clusters really prefers equal mass. But I see a population of second generation of quite equal mass. And I also see a lot of structure in one.
Yeah, well, okay, so, good question. So I can talk about a couple pieces of structure. So one very distinct piece of structure you can see, especially here, is this very sharp sort of cutoff in the sort of the dark blue generation 1 distribution. So that's from an imposed cutoff for where we put the parent stability mass gap, essentially. So it's probably not as sharp as this, obviously. It probably is blurry. But anyway, it's convenient here because it shows distinctly what is which. Okay, so the reason that we have so many more equal mass generation 2 mergers, so generation 2 here is both 1G plus 2G as well as 2G plus 2G. So these massive clusters, especially because, again, they have higher escape velocities, you're able to get a lot more 2G plus 2G mergers than you might usually get. So that's why that distribution in the 2G mergers is starting to shift a little bit more towards equal masses. Now, this is that statement I just said is specific to these massive clusters. Obviously, if you wanted to look at the full sort of cluster contribution in general, you would need to also include the lower mass things as well, et cetera. Yeah, it's hard. It's hard to see from a scatter plot. But which part are you talking about specifically?
I'm just wondering, like, they're not all like ranked up against equal mass. There's quite a lot of stuff.
Yeah. So if I plotted it as a contour, they are quite heavily biased towards equal mass things. Yeah. I mean, it's 1,000 plots I'm showing in a overlapping scatter plot. Yeah. Yeah. Good question.
Hi, Javier Roulette from Chicago. You said that the one example where it has an IMBH is not core collapsed.
That's
And
correct.
You mentioned that the IMBH might be responsible for this. This, I don't know, intuitively seems strange to me. So what are the mechanisms why having a massive black hole would heat it up?
Okay, so I want to first say the same caveat that omega sen is very clearly not a typical globular cluster. It's almost certainly a strip dwarf nucleus. So with that caveat in mind. So the way that an IMBH, this is not just like an inert IMBH in the center. It's almost certainly undergoing black hole mergers with lower mass black holes with other things. So an IMBH plus a little black hole merger is going to heat, the cumulative effect of many of these are going to heat the cluster in the same way that many stellar mass black hole mergers would dynamically heat the cluster. So I think it's very natural to suppose that clusters with a massive black hole, as well as probably stellar mass black holes as well, would be more conducive to having a large core radius.
Hans Holterix, MPIA. You had talked about the black holes seen directly in the local globular clusters, but in the end it felt a little bit more like basic motivational. Let's presume we had a much better census of the globular cluster black holes in the local globular clusters. What would it teach you about a plot like this, for example?
Okay, good. So thank you, because I skipped over this part, but I was going to talk about this. So how can we observe more of these is an open question. Well, sir, how can we observe better the ones that we do observe with just RVs? Because we only have a mass function. So Casey, where's Casey somewhere? Casey Lamb is in the back. Okay, so Casey and I and Kareem is involved in this as well. We have an HSC program right now to do astrometric follow-up of these RV sources to try to measure the actual mass of the black hole. So that's a really important first step, because you can see the mass function for these three. The one in the middle is maybe a little iffy, but the 4.5 and the 7.7 I think are quite robust. They're quite low mass, so how massive are these is an open question. This is an important constraint. The other really important thing is there's two, maybe three, but probably two, and that's sort of that's all of our observational evidence for black holes and clusters. So if indeed every cluster has black holes, there should be more of these. So can we find more of these? So let's see. So this is actually a program that I'm leading. This is Casey Carlisle, who's a grad student at UCSD. So we're leading a program with the Keck Cosmic Web Imager to try to find more of these in other Milky Way globular clusters. So there's sort of two components. We're doing targeted follow-up of known large radial velocity variation from MUSE. And then we're also doing sort of a blind search of additional clusters that have large core radii that we think probably have a lot of black holes in their center, to try to find more of these. So I think this is promising because, I mean, if we find another black hole or a couple other black holes, that'd be great, obviously. But even if we don't observe any, that's starting to put interesting, and that would start to make people like me uncomfortable, because the simulations predict quite clearly that these black hole star binaries should be there in most clusters. So if we're not finding these, of course there are sort of, selection biases, et cetera. But that starts to put interesting constraints on what the true population of black holes and clusters is, and then that obviously has implications for LIGO, et cetera. So yeah, work in progress.
Okay, yeah. Johan Samsing from the Niels Bohr Institute. So I'm just trying to understand, how can you, like, are there any way you can figure out what the relative merger rate is from these different clusters that you're talking about? I don't know if you mentioned that, but you argued that the young clusters could form this 24, 10, 11 type, right? But the older ones cannot. Does it already give you a hint on the rate that you'll get from the young clusters, and how does it factor into this mass function that you showed, which was explaining the low mass for the young clusters? But if you factor in the rate from the older ones, you should be able to get, you know, some idea of if it matches up with the total mass function.
Yep, that's definitely possible in principle. That's something we're working on. Yeah.
Okay, so what's the answer?
I don't have the answer yet.
Okay,
but yeah, I mean, that's the idea. Is, I mean, we have constraints just from looking at observations of clusters, what the like underlying relative rates of massive versus low mass clusters are. But you could do an independent constraint from LIGO just based on what, you know, what fraction of those would match mass.
So I learned during lunch that there seems to be pretty good indications for a redshift evolution of the merger rate, right? Would you expect that kind of redshift evolution from the younger clusters versus the older clusters that might not have the same evolution?
Well, yeah. I mean, younger cluster. Well, the very young high melicity things aren't really. There's not really much of a redshift evolution there because they were all born recently. So I think very high redshift things almost certainly must be generally, well, lower metallicity clusters at least. Okay. It could have been young because it's higher redshift.
Exactly.
But, yeah.
Okay. Okay.
Thank you. Martina Hrušnička. So I have a few questions, but let me ask about the diagram where you plotted the observed clusters and your simulations.
Yeah.
So is this, for your simulations, is this the final properties? No, the mass versus...
I'll go back a few more. Let's try not to...
So is this the set of final properties?
These are all present-day properties. So these are obviously final properties of Milky Way clusters, is all we can observe. These are final properties of the simulation.
So
now,
can you sort of show the evolution in this diagram?
Yeah, good question. So this is kind of showing this already because, again, these are 10 million year old young clusters. So the biggest thing that causes that, you know, affects the evolution of very young clusters is they lose tons of mass right away from the stellar evolution. So right away, these clusters are, once they evolve for another maybe couple hundred million years, are going to expand from just this mass loss from the stars. So that's why, if you know, maybe if you look closely, you can see, oh, well, these are actually more dense than Milky Way clusters. It's just because they're young and they haven't lost a lot of mass yet. So if I plotted like these, well, I don't have our simulations on here, but generally speaking, clusters expand over time because of mass loss and other mechanisms.
Mike Zevin, Adler Planetarium. Kyle, can you go back to Behemoth and Colossus?
Yeah.
Gonna run out of names for these things eventually. But so we've talked about this a little bit, but looking at this more, especially if you're looking at the high metallicity young clusters, if you were to do kind of more of a density map rather than a scatter plot here, you would see that we have many more second generation higher mergers at these higher masses, more equal masses than the ones that we've quote unquote definitively detected with LVK. So these should be ones that are louder, and preliminary studies that we've done show that there's not a huge measurement bias when you go to these higher mass ones compared to these lower mass ones from a LIGO data analysis perspective. So why are these kind of the first ones that we see with clear signs, definitive signs that they're hierarchical? And if we were to see more of these without seeing their higher mass counterparts in these types of models, especially because these big clusters contribute so much to the total black hole rate.
More of these versus these, you mean?
Yeah, or in the other plot where you're at the higher metallicity. Okay. So what would that tell us about these kind of large cluster models and the cluster models in general that are giving us hierarchical mergers?
I mean, there could be multiple things contributing. I mean, the formation history of clusters. Okay, so local universe, we observe things well, but the formation and the metallicity dependent formation history, we don't know. So that could easily, that's gonna change the relative values of all of these things quite a bit. Obviously, this is just everything in the history of the cluster, so it's not a very this alone is definitely not a one-to-one comparison with LIGO, because this plot is integrated over the history of the cluster, not just local universe. I think the other obviously really big uncertainty is the true cluster mass function, which we have talked about. This is assuming R is the Am's to black hole mass relation, which I would not claim is the true answer necessarily. So that would obviously also certainly affect the relative values of different parts of this parameter space.
All right, let's thank Kyle again.